There is a plant the size of a thumbnail floating in ditches and drainage canals across 3 continents that does something no land crop on Earth can do. It pulls nitrogen directly out of the atmosphere and converts it into fertilizer. No factory, no natural gas, no purchased input of any kind, just sunlight and open air. It doubles its entire mass every 2 to 5 days. It has been quietly running rice systems in China for over 1,000 years. And in a world spending $230 billion annually on synthetic fertilizers, that same plant remains almost completely unknown to Western farmers. That is not an accident. The global fertilizer market depends on you never asking why a fern that grows in standing water can replace the product they sell you in 50-pound bags. This is Azolla, a floating aquatic fern so small it covers a pond like green velvet. Scientists have begun calling it a biological miracle. The fertilizer industry has a different name for it. Nothing. Complete silence. That silence costs farmers billions of dollars every single year. The archive opens in the rice paddies of 7th century China. Farmers working flooded fields notice something. Wherever the green mat appears, the rice grows taller, darker, heavier at harvest. They do not understand why. They simply learn to encourage it. They carry it from field to field in baskets. They protect it over winter. They record their methods in agricultural texts that survive 1,000 years. By the Song dynasty, cultivation manuals explicitly instruct farmers to grow the fern alongside rice as a nitrogen amendment. This knowledge spreads through Vietnam, through Korea, through the lowland paddies of Southeast Asia. By the 20th century, the fern covered approximately 1.3 million hectares of Chinese rice fields. Not because governments mandated it, because it worked. Vietnam researchers eventually catalogued 30 distinct local strains, selecting for cold tolerance, salt resistance, and heat resistance. Different strains for different conditions. This was not folk superstition. This was a 1,000-year breeding program conducted without a single university, without a single patent, without a single corporate research budget. 24 generations of Asian farmers had solved a problem that the Haber-Bosch process would later claim to have invented. The Chinese knew it first. They just did not sell it in bags. The spread of Azolla cultivation across Asia was not uniform. Each region adapted the technology to local conditions and local needs. In the Mekong Delta, farmers discovered that Azolla thrived in the hot, humid monsoon climate better than any other region. They developed cultivation techniques specific to tidal freshwater rice fields where saltwater occasionally intruded. In the terraced paddies of the Philippines, farmers learned to manage Azolla density to prevent it from choking out the rice plants entirely. In Taiwan, growers selected strains that could tolerate cooler winters, extending the cultivation season. This regional adaptation represented genuine agricultural innovation happening at the grassroots level. Farmers were conducting field experiments, selecting for traits that mattered in their specific environments, and sharing their knowledge through informal networks that connected villages across river systems. By the time Western agricultural scientists began documenting Azolla in the 20th century, Asian farmers had already completed most of the basic breeding work that modern plant scientists would spend decades repeating. The knowledge was already written down, it was already proven, it was already working on millions of hectares. What was missing was not the science. What was missing was the commercial incentive to promote it outside Asia. Western agricultural development in the 20th century was built on the assumption that modern meant chemical, that progress meant purchased inputs, and that tradition meant backwardness. Azolla did not fit that narrative. It was traditional. It required no purchased inputs. It represented continuity rather than disruption. So, despite overwhelming evidence of its effectiveness, despite documentation in peer-reviewed agricultural journals, despite proof that it worked across multiple climates and cultures, Azolla remained confined to Asia. The West had already committed to a different path. Then comes the science that explains what those farmers understood intuitively. Inside every Azolla leaf, there is a cavity. That cavity houses a cyanobacterium. The scientific name is Nostoc azollae. This organism has lived inside Azolla without interruption for more than 50 million years. Not as an infection, not as a parasite, as a partner so deeply integrated that both organisms pass from parent to offspring together during reproduction. No other relationship like this exists between a cyanobacterium and a plant anywhere on Earth. The cyanobacterium uses specialized cells called heterocysts to crack molecular nitrogen out of the air and convert it into ammonia the plant can use. The fern feeds the cyanobacterium carbohydrates through photosynthesis. The cyanobacterium feeds the fern nitrogen, a closed loop, a system that needs nothing from outside except sunlight and water. Measured nitrogen fixation rates run from 1.1 to 3.5 kilograms per hectare per day. Annual productivity potential exceeds 1,200 kilograms of nitrogen per hectare per year. That is more nitrogen than most legume crops produce, more than clover, more than alfalfa, more than almost any biological nitrogen-fixing system humans have ever deployed. 1 hectare of Azolla ponds captures an estimated 21,266 kilograms of carbon dioxide annually, and it doubles its biomass in 2 to 5 days. You cannot engineer a crop that does this. The biochemistry took 50 million years to perfect. You cannot patent what nature already finished. The mechanics of this partnership reveal something profound about how life solves problems. The heterocysts in the cyanobacterium are specialized cells that create an oxygen-free environment where the nitrogen-fixing enzyme nitrogenase can function. Nitrogenase is one of the oldest enzymes on Earth. It evolved in early bacterial life forms when the atmosphere contained no oxygen. Organisms that could fix nitrogen had an enormous advantage. They could survive anywhere there was water and sunlight. They did not need to compete for scarce nitrogen sources. But nitrogenase is fragile. Oxygen damages it. So, cyanobacteria developed heterocysts as protection. Inside Azolla, the cyanobacterium has even more protection. The fern's leaf cavities provide shelter and stability. In exchange, the fern receives a constant supply of nitrogen fertilizer, manufactured on demand inside its own cells. The fern does not need to wait for nitrogen from decomposing matter or from the soil. The nitrogen appears where it is needed, when it is needed, in a form the plant can use immediately. This is not a metaphor. This is a functioning biological nutrient delivery system that modern agricultural chemistry is still trying to replicate through industrial processes. The Haber-Bosch process converts nitrogen gas into ammonia, which is then processed into various fertilizer products. The energy requirements are enormous, the carbon footprint is substantial, and yet the end result is less efficient than what Azolla accomplishes continuously with nothing but sunlight. A fern and a bacterium have engineered a system that outperforms industrial chemistry. They accomplish this without human intervention. They accomplish this over millions of years of coevolution. Every time a farmer applies synthetic nitrogen fertilizer, they are paying enormous amounts of money to do something that Azolla does for free, continuously, automatically, and with zero environmental damage. There is a chapter older than Asian rice farming. It sits in the geological record, not in agricultural texts. 55 million years ago, the Arctic Ocean was warm, tropical. The poles were forested. Carbon dioxide concentrations in the atmosphere were multiple times higher than today. Then something happened, a bloom. Azolla spread across the surface of the Arctic Ocean in a mat so dense, so continuous, and so sustained that it drew down atmospheric carbon dioxide on a planetary scale. Scientists call it the Azolla event. For roughly 800,000 years, the fern multiplied, sank to the ocean floor when it died, and carried captured carbon with it into sediment, layer after layer. 800,000 years of sequestration. The geological evidence shows atmospheric carbon dropped sharply. Global temperatures fell. The modern Ice Age climate began. A floating fern smaller than your thumbnail restructured the atmosphere of an entire planet. That is what the synthetic fertilizer industry is competing against. That is what the herbicide manufacturers and seed companies have collectively chosen to ignore. The most powerful biological carbon and nitrogen machine in the history of life on Earth, and it will grow in any standing water in any climate zone where rice can grow, which includes most of the places where 8 billion people now live. The implications of the Azolla event extend far beyond historical interest. Scientists studying past climate shifts have realized that biological processes can alter planetary atmosphere composition on timescales of centuries or millennia, not just on geological timescales of millions of years. If Azolla could draw down carbon dioxide levels dramatically when it bloomed across Arctic seas, could controlled cultivation of Azolla be used to address modern carbon dioxide elevation? Research is beginning to explore this possibility. Some scientists propose that large-scale Azolla cultivation in tropical regions could simultaneously produce nitrogen for fertilizer, produce biomass for animal feed, sequester carbon, and improve soil health. One study estimated that global Azolla cultivation could offset a significant percentage of agricultural emissions, while simultaneously reducing the need for synthetic nitrogen fertilizer production, which itself is a major source of industrial carbon emissions. The calculations are preliminary. The feasibility at global scale remains untested, but the theoretical potential is substantial. A system that feeds half the world's population while generating massive emissions could be partially replaced by a system that generates nitrogen while sequestering carbon. That transformation alone would reshape global agriculture. It would also eliminate a significant revenue stream for fertilizer companies, which may explain why Azolla research remains underfunded, despite the obvious potential. So why is Azolla absent from every agricultural extension bulletin in the United States? Why are there no Azolla inoculum stations at the farm supply store? Why does the average American farmer know the names of 30 herbicides and cannot identify the one organism that could cut their nitrogen bill in half? The answer is the same answer it always is. Azolla cannot be patented. It has been reproducing freely for 50 million years. No company can sell you next year's inoculum because Azolla produces its own inoculum continuously. There is no annual purchase, no dependency, no leverage. The Haber-Bosch process consumes enormous quantities of natural gas to synthesize ammonia. It feeds roughly half the world's population. It also generates massive carbon emissions. It also costs farmers $230 billion every year in inputs they must buy repeatedly, every season, without exception. That market disappears the moment farmers learn to grow nitrogen. Azolla grows nitrogen. Senegalese researchers tested it in the Saint Louis River Valley, a climate nothing like China, nothing like Vietnam. Farmers using Azolla reduced urea application by 50%. Yield still increased by more than 4%. Input costs dropped 33%. That is not a laboratory result. That is a farmer in Senegal with more money at the end of harvest. The fertilizer company does not want that story told. Agricultural extension offices in North America have published no guidance on Azolla integration. No government agency is funding large-scale Azolla research for food security. They are not publishing bulletins about it. They have simply made sure you never heard of it. The silence is the strategy. The mechanisms of this silence are worth examining. Agricultural extension offices in the United States are partially funded by state legislatures, but they also receive substantial funding and support from agricultural chemical companies. These companies donate equipment, fund research positions, and sponsor educational programs. It would be naive to expect these companies to promote a crop that eliminates the need for their primary products. Similarly, agricultural universities that conduct most of the research on farming practices receive grants from chemical companies. The funding directs research toward improving the efficiency of chemical inputs, not toward eliminating the need for chemical inputs. No scientist receives a grant to prove that their funding source's products are unnecessary. The structure of agricultural research and education in the West is built on an assumption that chemical inputs are essential. Any technology that challenges this assumption will struggle for funding and support. Azolla directly challenges this assumption. Therefore, Azolla struggles for funding and support. This is not a conspiracy. This is how systems work. The incentives are aligned in one direction. The people in those systems are not evil. They are simply responding to the structure they work within. But the result is that knowledge which could benefit farmers is systematically excluded from agricultural extension, research, and education. The farmers never hear about it. The researchers never study it. The universities never teach it. The technology remains confined to the regions where it was developed before the chemical industry became dominant. India never forgot purslane. China never forgot Azolla. Half the world is still using a technology that the other half was taught to overlook. Not because the technology failed, because it succeeded without generating revenue. A plant that fixes nitrogen from thin air, doubles every 3 days, suppresses weeds by blocking sunlight, reduces water evaporation from paddy fields, improves soil organic matter after incorporation, and asks for nothing except a pond or a flooded field, cannot be monetized. So it cannot be promoted. The fertilizer industry generates billions per year selling a product Azolla makes for free. That industry does not want you to know a floating fern has been doing their job for 50 million years. The agricultural universities that receive funding from chemical companies do not publish Azolla integration guides. The farm supply stores that profit from nitrogen sales do not stock Azolla inoculum. The entire infrastructure of industrial agriculture is oriented toward dependency. Azolla represents the opposite of dependency. It represents permanent nitrogen independence. You grow it once, it replicates. You apply it to flooded fields, it fixes nitrogen and decomposes into the soil. Next season, you collect more. The cost approaches zero. The nitrogen input cost approaches zero. That model cannot coexist with a $230 billion annual market. So one of them had to disappear. Farmers in China and Vietnam figured out which one lost. The practical applications extend beyond rice paddies. In Bangladesh, researchers have studied Azolla integration into fish farming systems, where the fern provides food for fish while simultaneously enriching pond water with nitrogen. The fish benefit. The farmer benefits through increased productivity. The nitrogen cycle intensifies. Similar experiments in India have explored Azolla as a livestock feed supplement, reducing the need for purchased animal feed while improving soil fertility in integrated farming systems. In parts of Indonesia, small farmers have begun experimenting with Azolla in vegetable production, where controlled flooding of certain crops allows Azolla cultivation in rotation with upland vegetables. The results suggest that Azolla is not strictly limited to rice production. It can integrate into diverse agricultural systems wherever standing water can be temporarily maintained. Each application generates local knowledge about strain selection, timing, and integration methods. This knowledge accumulates, spreads, gets refined. And yet none of it appears in Western agricultural research, Western extension bulletins, or Western agricultural education. The knowledge is simply not available where Western farmers could access it. Learn to identify Azolla. The leaves are tiny and overlapping, red-green or bright green depending on light intensity, covering still water like a thick carpet. In full sun, it turns reddish. In shade, it stays deep green. It floats freely on the surface and feels almost velvety to the touch. If you have a pond, a flooded garden bed, or even a large container of still water, you can grow it. It asks for nothing beyond water and sunlight. Collect a handful from any pond where it grows wild. Place it on standing water in a sunny location. Watch it double. Apply the fresh biomass to garden beds as a nitrogen-rich green mulch. Dig it into soil before planting. It decomposes rapidly and releases nutrients fast. If you grow rice, grow Azolla alongside it. The fern fixes nitrogen into the water and into the soil. The rice uses it. A single Azolla application has replaced up to 50% of the urea requirement in documented field trials. That is not a theoretical reduction. That is a measured result from real fields with real harvests. Stop buying nitrogen when nitrogen grows in your pond for free. The synthetic fertilizer industry spent 150 years building a system that convinces farmers fertility must come from a factory. It does not. It comes from a 50-million-year-old partnership between a fern and a bacterium that figured out atmospheric nitrogen long before humans invented chemistry. The plant is called Azolla. It is in the ditches. It is in the drainage canals. It is in every warm pond on 6 continents. It has been feeding rice civilizations since before written records. The fertilizer companies definitely know it exists. They are counting on the fact that you do not. If this information has shifted something in how you understand agriculture, follow along as we continue uncovering what institutional silence has kept buried. Enable notifications so you don't miss the next discovery. Your engagement, your views, your shares, your comments, all of it disrupts the quiet. That disruption matters. It spreads what the industry worked hard to keep confined. The systems that profit from farmer dependency are counting on your silence and your disconnection. Information like this exposes the architecture of that dependency. The vault opens again soon.